NASA's Goddard Space Flight Center in Greenbelt, Maryland. Naseem Rangwala, project scientist for the Sofia mission, and NASA Ames Research Center, Silicon Valley, California. We also have a special guest today, Sarah Noble, lunar scientist at NASA headquarters. And with that, let's get started. Paul?
Thank you, Felicia. It's great to be making this announcement today. Several studies have showed that water on the moon's surface is in its permanently shadowed craters. Today, we are announcing that for the first time, water has been confirmed to be present on a sunlit surface of the moon. This is exciting because the expectation is that any water present on a sunlit surface of the moon would not survive the lunar day. This discovery reveals that water might be distributed across the lunar surface and not limited to the cold shadowed places near the lunar poles, where we have previously discovered water ice. The discovery was made with Sofia, NASA's airborne observatory, which flies a 100-inch or 2.5-meter telescope high in the Earth's atmosphere to study the universe in the far infrared part of the electromagnetic spectrum. The water molecule consists of 2 atoms of hydrogen and 1 atom of oxygen. Sometimes water is called H2O. Previous observations detected hydrogen through hydration on the lunar surface. Sofia's infrared spectrometer was able to identify the chemical fingerprint unique to the water molecule, showing that the previously detected hydrogen is in a water molecule and not in some other kind of hydrogen-containing molecule. This discovery raises new questions about how water is created and how it can persist in the harsh, airless conditions of the sunlit lunar surface. This discovery, of course, is of more than just scientific interest to NASA. With the Artemis program, NASA will land the first woman and the next man on the moon in 2024 and establish a sustainable human presence by the end of the decade. At the moon, we will prepare for human exploration of Mars. Water is a precious resource in space, but we want to know everything we can about water on the moon. One of the things we don't know yet is whether the water detected by Sofia on a sunlit surface is accessible for use as a resource. With that introduction, I'm now going to turn it over to Casey Hannibal, who is the lead author of the paper published today reporting this discovery. Casey?
Thank you, Paul. So prior to this discovery, for about a decade, we knew that there was some form of hydrogen on the sunlit surface of the moon based on previous spectroscopic observations. Spacecraft studied the moon in the infrared at wavelengths of 3 microns and could not differentiate between the water molecules and their close cousin, hydroxyl. Hydroxyl is actually the active ingredient in drain cleaners. Hypothetically, if drain cleaner were on the moon, we could not tell the difference between the drain cleaner and water using the 3-micron wavelength. However, if we study the lunar surface at a wavelength of 6 microns with Sofia, the water molecule has a distinct chemical fingerprint that hydroxyl does not have. The 6-micron fingerprint requires the bond between 2 hydrogen atoms and 1 oxygen atom that only exists in the water molecule H2O. Sofia's unique position above most of the water in the Earth's atmosphere allowed us to look for the 6-micron fingerprint on the sunlit moon. This observation finally allowed us to definitively determine that water molecules are present on the sunlit surface of the moon. We found the water in the moon's southern hemisphere at Clavius Crater and its surrounding region. Clavius is one of the largest craters visible from Earth. At this location, the data reveal a water concentration of about 100 to 400 parts per million. That's roughly equivalent to a 12-ounce bottle of water within a cubic meter of volume of lunar soil. But our observations with Sofia only sense the very surface of the moon. To be clear, this is not puddles of water, but instead water molecules that are so spread apart that they do not form ice or liquid water. The water that we observe has 2 potential sources. It could be either from the solar wind or micrometeorites. The solar wind delivers hydrogen to the lunar surface that reacts with oxygen in the soil and forms hydroxyl. During micrometeorite impacts on the moon, this pre-existing hydroxyl can be converted into water by combining 2 hydroxyl molecules together in the high temperatures from the impact. Many of these same micrometeorites may also contain water of their own that can transfer to the moon. What's interesting is that without a thick lunar atmosphere, water on any hot sunlit surface of the moon should be lost to space or find its way to the lunar polar cold trap. Yet somehow we're still seeing it on the sunlit moon. We think the water is trapped within glass beads within the soil that forms during the micrometeorite impact. These glass beads are about the size of a pencil tip and protect the water from the harsh lunar environment. Understanding the source of water and its retention helps piece together the broader history and role water plays in the inner solar system and on other airless bodies like asteroids, and may have implications for human exploration. Our next speaker is Jacob Lucha. Jacob?
Thank you, Casey. The Sofia results discussed today are very exciting for us in human exploration. This discovery is a great example of science and human exploration working hand in hand. This is a multidisciplinary science approach to collect data that will also help enable human exploration. Understanding where the water is on the moon will help us prepare to send astronauts to the lunar South Pole with our Artemis program. But you might ask, why does water matter to Artemis? Well, it's far easier to travel when you don't have to carry everything with you that you might need for the entire trip. For instance, here on Earth, if you can depend on resources throughout your trip and at your destination, things you might get at a gas station or a restaurant or hotels or campsites, then you can be much more efficient with what you pack. If it comes down to packing water or your favorite book to read, well, you'll have to take the water to survive. Water is extremely critical for deep space exploration. It's a resource of direct value for our astronauts. Water can be turned into oxygen for them to breathe. It could be a fuel supply that they use later. But obviously, it can be water they can drink, or you could use it for other purposes. But water is heavy, and therefore it's expensive to launch from the surface of the Earth. Anytime we don't need to pack water for our trip, we have an opportunity to take other useful items with us. For instance, payloads to do more science. So you can imagine easily being able to use water that is already at the moon would be a big help for us in exploring the moon with our astronauts. We know there's water at the moon, but we don't know exactly how accessible lunar water is for our future explorers. Knowing where we can find water is a good first step, but we need to know more about the water to understand if and how we can use it for both science and exploration. We know that water exists in some of the darkest and coldest locations on the moon, inside craters that have never seen sunlight. Those cold and dark environments are difficult to reach, and they can be even harder to work in for long periods of time. So finding water that's easier to reach is really important to us. This could involve finding easier to reach small craters that have the water, or, as these Sofia results show, that we can find water outside of these craters. Understanding the state in which the water exists is quite important. If it's locked into the glass beads, as Casey mentioned, it may require more energy to extract it. If the water is mixed up in the soil, it might be a little easier. Regardless, knowing more about that water, how it gets there, the form in which it's present, how much of it exists, whether it moves around, all of this is very useful information for planning possible resource utilization on the moon. It's also important to understand how stable the water is and how easily disturbed or lost it might be, as well as whether or not it might be replenished over time, or if it's lost for good from the location once we sample or use it. Future missions like NASA's Volatiles Investigating Polar Exploration Rover, or VIPER, will be looking for water directly on the surface and up to a meter below the surface to help make the first water resource maps of the moon. You can see that this exciting discovery leads to many new questions about water on the moon and our future science and exploration activities. And now we'll hear from Naseem Rangwala, Sofia's project scientist.
Thanks, Jacob. As Paul mentioned, Sofia is an airborne observatory. By flying at high altitude, up to 45,000 feet, Sofia is able to get above 99.9% of the water vapor in Earth's atmosphere that is blocking the infrared light from space. Specifically, for this discovery, Sofia allowed us to detect water on the sunlit surface of the moon without contamination from terrestrial water. Sofia carries an instrument that is able to pick up the specific wavelength unique to water molecules at 6.1 microns, as you heard from Casey. In fact, Sofia is currently the only telescope on or off this world that can provide remote access to this unique chemical fingerprint of water at 6.1 microns. Normally, we study distant and much dimmer objects like black holes, star clusters, and galaxies. This was actually the first time Sofia observed the moon, and we did it as a test case. Because the questions surrounding the moon's water were so compelling, we decided to use the observatory in a way not previously imagined. So in August of 2018, we decided to try a test observation on the moon. This discovery was made while we were flying over Nevada on our way back to our home base in Palmdale, California. What was essentially a test far exceeded our expectations. Now that we know we can do this, and given the importance of understanding the distribution of water on the moon and the origin of water in our solar system, we are planning more flights with Sofia to collect more data. We are very excited that these follow-up observations will look for water in more sunlit locations to better understand how water is created, stored, and moves across the lunar surface over time. These observations will add to the data that NASA's next moon rover, the Viper mission, will collect to create the first water resource maps of the moon. Back to you, Paul.
Thanks, Naseem. NASA's space observatories allow us to study the universe in ways that are impossible from the ground. And although Sofia is not a space observatory, it's an airborne observatory, it does allow us a view of the universe in the far infrared that is impossible from the ground because the water vapor in the Earth's atmosphere blocks this part of the electromagnetic spectrum. Today, we are announcing an important discovery by Sofia, that the previously detected hydrogen on the sunlit surface of the moon is located in water molecules. This discovery raises new questions about how water is created on the surface of the moon and how it can persist in the harsh, airless, sunlit conditions of the lunar surface. Knowing how much water is on the moon and how we might be able to use it in the future supports NASA's long-term human exploration goals into deep space. NASA will continue to leverage all of its assets, including Sofia, the world's premier airborne observatory, to contribute to the success of the Artemis mission and NASA's human exploration program. Alicia?
Thanks, Paul. Media resources for this announcement is available on nasa.gov/Sofia and can also be found on our press release. We will now start the question and answer session. Sarah Noble, headquarters lunar scientist, will also be joining us to cover your questions. We will limit everyone to one question. Our operator should identify you, but if not, please identify yourself, your media affiliation, and then direct your question to a specific panelist if possible. For those dialing in, push *1 keys on your phone to be placed into queue. To ask a question using Twitter, please use the hashtag #AskNASA. And with that, let's begin. Let's start with Jeff Faust from Space News.
To the moon, whether they are orbiters or some of the landers beyond, obviously, the Viper rover, might be used to better characterize the water signal that you saw with Sofia. Is there anything currently on the books that would help in that regard? Thanks.
This is Jake. I'm sorry, we missed the very beginning of your question. Could you maybe restate it, please?
Sure. Let me try and summarize. Are any of the upcoming missions, whether they are orbiters or landers, including payloads on CLIPS landers, useful in helping to better characterize the water signal you saw with Sofia? Thanks.
Yeah, I can give you a little background on some additional CLIPS capabilities that we're looking at. The CLIPS flights, or commercial lunar payload services, will leverage capabilities of industry partners to quickly deliver scientific instruments, technology demonstrations to the moon. As part of that, NASA will be sending dozens of science investigations and technology experiments to the surface that will help us find and potentially extract later resources on the moon. So just an example of some of these that we're looking at moving forward. One would be the mass spectrometer observing lunar operations, or MSOLO. MSOLO will identify low molecular weight volatiles. It can be installed to either measure the lunar exosphere or even things like spacecraft outgassing and contamination, because we also want to understand what our presence might be doing to the water and the precious volatiles there. So data gathered from MSOLO will help determine the composition and concentration of these potentially accessible resources. Another example would be a neutron spectrometer system, NSS. NSS will search for indications of water, ice near the lunar surface by measuring how much hydrogen-bearing materials are at a landing site and help determine the overall bulk composition of the regolith around it. Another example would be the near-infrared volatile spectrometer, or NIRVIS. NIRVIS will measure surface and subsurface hydration, carbon dioxide, methane, all resources that could potentially be mined from the moon and used by our future explorers. They also help map surface temperature changes at the landing site. And we mentioned VIPER earlier. We also have another activity that will be going ahead of VIPER. NASA's awarded Eclipse provider Intuitive Machines a task order to fly the Polar Resources Ice Mining Experiment, or PRIME-1. So PRIME-1 is a drill combined with a mass spectrometer, and it'll be heading to the moon late 2022. So this is a precursor drill, and it will fly with VIPER, which will fly. It is a precursor to the Trident drill that's going to fly with MSOLO on VIPER. So this is going to give us an example of how exactly to use the more enabled VIPER mission when we get it there. So we do have a series of activities and payloads that are already set up to help us start measuring this and understand more about the environment and the volatiles there.
Great, thank you. Next question is Marcia Dunn from AP. Oh, sorry. Yes, Marcia Dunn from AP.
Yes, hi. Can you hear me?
Yes.
Hello? Yes. Yes, this is for the lead author, Ms. Hannibal. Could you tell me, please, how much, over how much area of the moon did you detect these molecules, the water molecules? If you could give some sense of how vast an area, how small an area, and how many molecules are we actually talking about, in the thousands, millions? I'm just trying to get a handle on how big and how much.
Yeah, so the Clavius Crater is the largest crater observed from the Earth, but it's not that big. When we looked at the moon, our observations extended from about a 50-degree latitude down to about 75 degrees in latitude on the moon. So we only covered a few degrees on the moon. Also, the abundances that we measured are only 100 to 400 ppm of water, which is not a lot. Like I said, these water molecules are not interacting with each other. They are individual molecules incorporated into these glass beads, so they're not in a form of ice or liquid.
Thank you. Next question. We have David Curley from the Discovery Channel.
Thanks for taking the question. You kind of touched on it there. I mean, this is an amazing discovery, but how much is there? Will it matter? Will it provide for astronauts if we need to mine it? Thank you.
Casey, I think maybe you could reiterate the amount of water.
Yeah, so the amount of water is roughly equivalent to a 12-ounce bottle of water within a cubic meter of lunar soil. But this, instead of being at a volume, this is spread across the surface of the moon. Whether or not it's usable for mining, I will turn over to Jacob.
Yeah, thanks, Casey. And this is, this is the core part to the question, right? And I think several of us hinted at this, is that we really need to understand more about the water that's present. So we need to understand what form it's in. We need to understand how much of it there is. And this complement of approaches, of measurements that we can make, some of them look at just at the surface. Some can look deeper below the surface. Some see water in different forms than in other forms. We need to gain that broad picture of what the resource stock really is at the South Polar region. We also need to understand how we can not only approach it as a resource, but how we can also use it as a science resource, because that ice also carries with it much information about evolution of the solar system, evolution of the sun, evolution of the moon-Earth system. So, it's hard to answer the question straight up, is this discovery going to provide us with enough water to do anything specific? It's part of a process in moving forward and understanding volatiles and volatile cycles on the moon. And this is an important discovery because now we know that that water does exist outside of some of these places in these dark craters that are really hard to get into and really hard to operate in. So this might be an avenue for us to get to water a little bit easier.
Thank you. Next, I believe we have Joey Roulette from Reuters.
Hey, question for Paul and Jacob, kind of similar to what was asked before, but what will it take to know whether the water molecules can be turned into usable resources to support the Artemis program, like drinkable water, ingredients for rocket fuel, etc.? Do you think we'll know this from more remote observations, or will we have to rely on future robots or probes on the ground on the moon? Thanks.
I can give my my first shot at answering that question. We already listed off a handful of additional payloads that are planned to go to the lunar surface. I think it's critical that we combine remote observation, which can give us the broad context. So, observations from Sofia, coupled with other observations that look more broadly at the moon, can tell us regionally where we see those signatures. But then we need to also get on the ground and sample. So we have, as I mentioned, the Viper mission is heading that way. And, I hope that you can see that this is kind of an iterative approach. So, for instance, we're sending the Prime 1 drill to help us understand better how to approach it when we get Viper there. That's a more capable vehicle. So, answering the question exactly when we'll know is difficult. What I can say is that from a in situ resource utilization perspective, we have multiple approaches to extracting the water, multiple activities that are underway. And as we learn more, we'll know better which of those to develop further so that we can follow that approach. And it may be that there's multiple approaches because the water will be in different forms in different places. It may be more accessible. We also, again, have to learn just simply going up to the water, are we going to be disruptive to it to the point that we then can't use it? So, each one of these lessons helps us learn better how to query the lunar environment, the lunar surface on our next step moving forward.
Thank you. Next, we have Kenneth Chang from the New York Times. Kenneth? Hello, Kenneth, are you on? Okay, before we go back to Kenneth, let's go ahead and take some Ask NASA questions. If you would like to ask a question using Twitter, please use the hashtag AskNASA. So we have a question from Liam Parker asking, what volume of water is found and does it suggest life may have been present on the moon previously? Sarah, can you talk about that?
Sure. So we covered a little bit about how much water is there. It's not a lot. And it's also water by itself is really not enough. There are other ingredients necessary for life. And the moon is frankly a really harsh place. The radiation environment, the lack of an atmosphere. There are lots of reasons we can talk about that where life is just not a thing that we think could have ever been possible.
Thank you. Let's try to jump back to the Q&A. Kenneth, are you available?
Yes, can you hear me now?
Yes.
Sorry about that. So I just want to clarify a few things. In 2009, there was data from Chandrayaan-1 about water in the sunlit area. Is this a confirmation of that, confirming that it's water and not hydroxyl, but otherwise similar? And was there a confirmation of water in the deep craters from the L-cross, or is there also that ambiguity between H2O and hydroxyl?
Hi, this is Casey. So I can take the first part of that. The observations from 2009 with M-Cube on the lunar surface were of the 3-micron band, which could not distinguish between hydroxyl and water molecules. What our detection today on the sunlit moon is saying is that at least part of what M-Cube detected is in the form of molecular water. Maybe somebody else can take the L-cross part.
Sure, let me jump in. L-cross did in fact find water, but that was of course looking in a permanently shadowed region. So the difference here is that we're now seeing it in sunlight as well.
Great, thank you. Next, we have Christopher Cokians from Sky News Canada.
Yes, can you hear me okay?
Yes.
Okay, and it's Coquino, so it's an odd name. No worries. First, congratulations to the team. And then a question about the map, the water map of Clavius. And did you see any evidence of movement of these molecules over time? In other words, these apparent glass beads that are containing these stray water molecules, are they breaking down? Are they moving at all due to solar wind or micrometeorite impacts? So was this, do you see a process? Is the map dynamic at all, or is that something to look for in future missions?
This is Casey. Yeah, that is definitely something that we are going to be looking for moving forward with continuing observations with Sofia. With the current data, it's just a snapshot in time of one location at one time on the moon. So we need, in order to understand the mobility of water and if it's moving and how it's really stored, we need more observations of different lunar phases to really be able to get at that mobility problem of water.
Great, thank you. Next, we have Leo Enright from Irish TV.
Thanks very much. I'm wondering about the source of this water. You mentioned one possibility as glass beads on the surface being impacted by the solar wind. Now, I'm afraid with this question, but I was actually in the science support room in the Mission Control Center during Apollo 17 when they were at Shorty Crater. And I will never forget the scenes in that room when they found orange soil, because everybody in the room believed that that meant water, and they were devastated, many of them, though they're scientists, when they discovered, well, maybe it wasn't. I'm wondering, could those be exactly the beads that you're talking about?
Hi, this is Casey. So those are actually different kinds of beads. Those are volcanic beads that were erupted during a volcanic process on the moon. The glass beads that we're talking about are little beads that form when a micrometeorite impacts the moon and melts part of the lunar surface. It melts it and could either deliver the water or form water from pre-existing hydroxyl, which then cools to form a little, what we are calling little glass beads. So there's the ones that they found on Apollo and the ones that we're talking about here are different beads. We do think that the Apollo glass beads like Apollo found may concentrate water, and hopefully we can do observations of the Apollo 17 site to possibly detect water at that location with Sofia.
And if I may cheat and ask a follow-up, I'm particularly interested in the instrument that you were using. It's my understanding that it was designed and built by the Andor Company in Belfast in Northern Ireland. Is that correct?
I'm going to pass this one on to Naseem.